Hello everybody and welcome back. Today we are going over Unit 4, Lesson number 2, and this is our unit on the water table. So yesterday we started our water unit and we talked a little bit about just the water cycle and also surface water. So remember, examples of surface water are going to be things like lakes, rivers, streams, ponds. Any water that is above the surface of the earth is going to be surface water. And then we talked about the actual water cycle itself and the different steps of the water cycle that we need to know. Today we are going to move on and we are going to talk about the water table. So yesterday our focus was on surface water. Today we're going to talk about groundwater and the difference between surface and groundwater. So as always, you should have downloaded your interactive notebook pages for today, and we are just going to jump right in. So we've already talked about porosity versus permeability, but we're going to go over it a little bit more in depth right now. So in terms of groundwater storage, remember water becomes groundwater when it infiltrates into the ground and then percolates, which just means it starts to seep further into the ground. So puddles, remember puddles would be considered surface water. They disappear partly by evaporating into the atmosphere, which will eventually condensate into clouds, and partly by percolating into the ground. So percolation/infiltration is just the seeping of the water into the ground. Earth materials, so sand, clay, silt, and rocks, are not totally solid. They do contain small openings or pores. So all these little cracks in between our rocks are known as pores. The percentage of pore space is called porosity. So the more pores that a substance has, the easier the water is going to pass through. So a lot of water is actually stored in the pore spaces of rocks and sediments. So when we talk about groundwater and where the groundwater is located, it's going to be in between the pores of these different materials. So just a reminder, porosity is the amount of water that can be stored in the pore spaces in the rock or sediments. And this includes things like faults and also caverns, which are just like caves. Permeability is a material's ability to release water, so the ability for water to pass through. So if pore spaces are too small, the water cannot pass through and it's considered to be impermeable. So here on this image, we've got some sediments that are very tightly packed, so there's no pore spaces, so that's not permeable. Here we've got some unconnected pore spaces. So water can sit in here, but it has trouble passing through. So it's porous, but it's not permeable because the water can't move through it. And then the connected pore spaces, when we say the pore spaces, it's the spaces in between. This is porous and permeable. So the water can go through the spaces and run through. Now, when we talk about groundwater, we have to talk about our water table. And our water table is going to be the upper limit of something called the zone of saturation. If we think about this word for a minute, saturation, if you think about a sponge and you start to run it under a sink and it gets really full and eventually it can't hold any more water and it starts to leak out, that's when the sponge is saturated. It's saturated at its maximum point of being filled. So the water table is going to be the upper limit of this zone of saturation. And so there's a couple zones we have to know about. The zone of saturation is actually the second one here in our presentation. This is also known as an aquifer, and we'll talk about aquifers a little bit here in just a second. But basically the zone of saturation is the pore spaces in the material where there is water. So the water within the pores of the zone of saturation is groundwater. Remember, groundwater is just underneath the Earth's surface. So the zone of aeration, so if aeration, think of air, this is the unsaturated zone, and the pore spaces are filled with mostly air. So zone of aeration, there's air, and then the zone of saturation is filled with water. And the water table is just that upper limit of the zone of saturation. So here's just a picture of what we would look at in our water table. So we have precipitation, and remember, some of that precipitation will run off and run into lakes and streams, and some of it will infiltrate and percolate into the ground. So we have our soil zone here, so this is where our dirt is. And then as this precipitation drips down, it will recharge the water table. So when we say recharging, if the water table gets recharging, it's just water is added to it, okay? So the saturated zone is where there is basically all the pores are filled in. So this is where the groundwater is. So the saturated zone below the water table is where we actually have the groundwater, where it's located between the pore spaces. And then up here in our soil zone where there is no water, it's unsaturated. So the unsaturated zone, or the zone of aeration, is where there is no water. And again, the zone of saturated is where the water is located. So the depth of the water table will vary depending on local conditions. So stream valleys, where there are lots of streams located nearby, the water table would be only a few meters deep. And in wetlands, the water table is right at Earth's surface. And the reason for that is because we went over briefly yesterday, a wetland is an area that is mostly covered by water. So it's mostly saturated, which means the water table will be very high. In hilltops or dry regions, the water table can be hundreds of meters or more beneath the Earth's surface. So you would have to drill down very far to get to the water. And the water table can vary too. It's not just one stable position all year long. It can rise with wet seasons and it can drop during dry seasons. And we'll talk about a well and how we get our water here in just a few minutes. So we need to talk about how we get our water. So that comes from aquifers, springs, and wells. So an aquifer is just permeable underground layers through which groundwater moves. Aquicludes that are a part of aquifers are impermeable layers of rock. So aquicludes are going to be the places where rock cannot pass through. So the groundwater tends to discharge or erupt at Earth's surface where an aquifer and an aquiclude will come into contact. And these natural discharges of groundwater are called springs. So basically, an aquifer will run into an aquiclude and then the water can't pass through, so instead it's forced up and it will come up through a spring. There are two types of aquifers we need to know about, confined and unconfined. So in an unconfined aquifer, the water will rest on an impermeable layer. So the ground above it is permeable and it can be refilled from rainwater that will infiltrate. So in an unconfined aquifer, the water is sitting on top of an impermeable layer so it can't pass through, but precipitation can recharge it by flowing through the soil. And then in a confined aquifer, the water is trapped between two impermeable layers and the water will become pressurized. This cannot be refilled from rainwater infiltration. So if you think of yourself, if you were confined in a small space, you would have, you would be trapped in on all sides. So confined aquifers, the rainwater will not be able to reach down into it. Now, the well that you build will depend on what kind of aquifer you are on top of. So a regular well, you just drill down into the water table and can draw water out through a pump. And then in an artesian well, which would be at a confined aquifer, because the water is pressurized, if you drill into it, the water will rise under its own pressure. So a regular well is in an unconfined aquifer, and the water will need to be drawn or pumped out. So, and then here's an example. So here we have an unconfined aquifer. Again, this would be the confining bed. So this would be that impermeable rock. So it's unconfined on the top because it's not in between two impermeable layers. The water from the rain can pass through and recharge it. This confined aquifer, however, has two of these impermeable layers. And therefore it is confined because there's no way for the rainwater to come down, seep down here, and recharge it. Okay, and these confined aquifers form over time. So, we could have the water table was here and this was once an unconfined aquifer, but over time we got, layers of clay and very non-porous sediments building on top in order to form this confined aquifer. So water table aquifers are unconfined and unprotected, are easily polluted. So this is something to keep in mind, because anytime we have surface pollution or runoff pollution, it can get into these water tables. So the surface spills of pollutants often reach the water table and spread throughout the aquifers. This is dangerous because this is where we get our drinking water. More reliable, less easily polluted water supplies can be found in deeper aquifers called the confined aquifers, which are sandwiched between the two aquicludes. And then the aquicludes, again, are just the barriers. This slide is basically telling you kind of a repeat of everything we just went over. So with a spring, the average length of time that groundwater remains underground is several hundred years. It will move slowly but continuously through the aquifers and eventually return to Earth's surface. In some cases, this will actually be against the force of gravity. So in most cases, the groundwater emerges wherever the water table intersects Earth's surface. The exact places where groundwater emerges will depend on the arrangement of the aquifers and the aquicludes in an area. So remember, typically we get springs where we have aquicludes and aquifers meeting, and those impermeable layers meeting. So groundwater tends to discharge at Earth's surface where an aquifer and an aquiclude come in contact. These natural discharges of groundwater are called springs. So the springs will occur in various places, such as the edges of valleys and also the edges of water tables near the surface. The volume of the water will vary from the flow of a small spring to the rush of a large river. So again, this will just have different factors in terms of it. So here we've got an anatomy of a spring. So the spring is here where this water that was trapped underneath the aquifers eventually comes up and emerges at the surface. So wells, when we talk about wells, they are holes dug or drilled deep into the ground to reach a reservoir or groundwater. And then to produce that water, a well must tap into an aquifer. So we have to make it to an aquifer in order to get the water for a well. The simplest wells are those that are dug or drilled below the water table into the zone of saturation and into what is called a water table aquifer. So keep in mind that the water table can go up and down. My grandparents, they lived out in the country and they actually had a well. So they were on well water. And one summer we had a really bad drought and the water table fell and they didn't have water for a while because it fell below where their well was dug and they were having issues getting water. So there are some issues with some wells. So we can have overpumping of a well, and that can lead to something called a cone of depression. And basically what will happen is that if the recharge does not keep pace with the groundwater withdrawal, the water table will continue to drop until the well goes dry. So overpumping is an issue with the wells. And this just shows you where the wells are. And then this cone of depression is where we get the overpumping and the lowered water table. An artesian well, again, this is you get an artesian well between a confined aquifer. So basically these are pressurized from their own confinement. So when the rate of recharge is high enough, the pressurized water in a well drilled into a confined aquifer may spurt above the land surface in the form of a fountain. So again, artesian wells are pressurized on their own, and basically you do not have to pull the water out of them. So a spring that discharges pressurized water is called an artesian spring. So the last thing we're talking about today is salt. So water is undrinkable when salt content's too high, and salt pollution is a very real issue when we talk about overpumping. So the overpumping of wells can cause the underlying salt water to rise into the wells and contaminate the freshwater aquifer, which is not good because obviously it can make you sick. And this is something called saltwater intrusion, and this is going to be the focus of our independent practice today.